Good morning. My name is Michael Wilson, and today I'm presenting my paper, Applying Modern Software System Design to Small Satellite Development and Operations. I recently graduated with a degree in computer science from the University of Michigan, where I worked in the Michigan Exploration Lab, or MXL, a multidisciplinary research lab focused on the innovation surrounding high-altitude balloon and small satellite design. In early 2018, MXL was developing the prototype for our MQ-9 or MC-9 mission. At the same time, we discovered that we could leverage the work of SatNOGs, a federated global ground station network, to increase our operational capacity for one of our existing spacecraft, the GeoCape ROIC In-Flight Performance Experiment, or GRIFFIX. We were also finishing the final verification and delivery of the Extended Tandem Beacon Experiment, or ETBEX. Unfortunately, our previous operation system was lost due to backup failures, so we needed a system to both augment our spacecraft development and our operational capabilities while we worked with 6 satellites, flight units, and development units between the 3 missions. Initial work for this system began in early 2019. We started writing a set of Python scripts that aggregated received packets from both the SatNOGs API and our own ground stations. These packets were decoded and dumped into Elasticsearch, a NoSQL database commonly used for analyzing time series data such as server logs. This allowed us to view spacecraft telemetry as time series graphs on a dashboard, which was a crucial first step for realizing what features we wanted from an operation system. However, it was not until ETBEX launched on SpaceX's STP-2 mission in June of 2019 that we had time to take a step back and architect a more thorough system. We decided that an effective and lasting solution should enable the following goals. Firstly, the system should not only enable, but mandate reliable, thorough testing of all of our software systems. It should also enable us to rapidly prototype new features while maintaining a stable system. In a university setting, it is also vital that the system supports efficient knowledge transfer as students enter the lab only to graduate in a few years. In addition, for MXL to continue to innovate, maintenance and operation tasks should be automated to create more time for analysis and developing new ideas. Lastly, an effective system should provide total operational visibility, which means that all team members, experienced or new, should have insight not only into the status of the system, but also into how other members are interacting with the system. These goals are achieved using modern software system design. The 3 core principles of modern software system design are that applications in the system should be small. That way, the system can be broken down into granular, easily tested, and easily understood components. Applications or services in the system should also communicate over a common interface, the network. This not only allows applications to be distributed and therefore resilient in the face of failures, but it also makes services easier to manage and scale individually. Finally, applications and the development process should be developer-oriented. They should follow simple architectures that engineers can easily contribute to and improve. In the university setting, this point is especially key for facilitating knowledge transfer. For our team, the application of these principles toward a distributed satellite operations and development system resulted in the creation of the MXL Integrated Data Analysis System, or MIDAS. In this diagram, you can see that while MIDAS has grown to incorporate many components, we have ensured that we follow the 3 principles of modern software system design. MIDAS is comprised of small, independent services, each with its own specific function. We use Docker, a popular containerization platform, to distribute these services across multiple servers, allowing them to communicate over the network. Containers, a form of process isolation, commonly described as lightweight virtual machines, isolate our individual services as if they each existed on their own physical hardware. We have found that running applications in individual networked containers has allowed us to both manage each service independently and quickly add new services as we learn and experiment. I'll now describe the architecture in more detail by focusing on 4 areas of our operations that Midas has improved. These are telemetry, aggregation and analysis, ground systems and satellite communications, systems monitoring and development, team collaborations, and communications. We'll see how Midas's system design has benefited MXL. Similar to our initial work, Midas aggregates telemetry data from 2 main sources, SatNogs and our own ground stations. Midas extracts data from these 2 sources, transforms it into a common format, and loads it into the appropriate data stores. In this case, a SQL database and a NoSQL database. This is what's commonly referred to as an extract, transform, load, or ETL pipeline. Once the data is in these stores, a variety of sources can access it, including Grafana, Hasura, and Jupyter Notebook, Cerebro, and our own custom dashboards. In order to access these tools, Midas users must first log in with their University of Michigan Google account. Requests are then authenticated and proxied to the appropriate service. For example, if logged into grafana.mxl-ops.engine.umich.edu, users are directed to our Grafana dashboard, which is used to create displays like this. Here, we see a time series graph of critical temperatures from the GRIFX CubeSat over the past 4 years. In the past, researchers would have had to manually load and graph these hundreds of thousands of data points. But using ETL pipeline techniques I've described, in tandem with tools such as Grafana, we can generate responsive graphs on the order of milliseconds. We also use a service called Hasura to generate a graph query language or GraphQL server. GraphQL lets our users experiment on our data using an intuitive query language. For example, the query on the left asks for a list of passes over ground stations. It specifies various parameters and orders the results by acquisition of signal time, and also limits the results to 5. The blue fields of the query on the left correspond directly with the query results on the right. GraphQL enables the user to ask for the acquisition of signal time, the ground station name, the spacecraft name, and the number of packets received during that pass, all in one simple query. We use these queries across our other services for easy and powerful data access. For extended analysis, we can use those queries to load data into Jupyter Notebook, where it is manipulated in Python. This heat map, generated in Jupyter, shows power generated per solar panel from one of the ETBEX units in orbit from January to April of 2020. In addition to providing analytical functionality to MXL, Midas provides increased operational commanding capability. Midas integration with SatNogs gives us access to hundreds of ground stations around the world, and MXL operators can therefore schedule downlinks of data over active ground stations. On orbit, our satellites send out telemetry data in a beacon every 10 seconds, but they only pass over our ground station at the University of Michigan for a small percentage of the day. For this reason, our flight spacecraft log and compress data into archive files. Our GRIFX satellite currently stores more than 5 years of historical telemetry beacons from orbit, but until Midas was created, we did not have a way to quickly downlink and analyze this archived data. These downlinked files result in an invaluable 2 orders of magnitude increase in our data resolution. We monitor the progress of various downloads on our file dashboard, as well as verify the integrity of files using an MD5 checksum. I've shown how our service independence, that is, keeping our applications small and networked, has provided some useful tools for our operators. Now I'll discuss how Midas has stayed developer-oriented. Midas stores all logs and metrics from its Docker containers in Elasticsearch, which allows us to closely monitor its health. So just as we have telemetry and operations for our spacecraft, we now have them for our ground systems as well. The key benefit of systems like Grafana is not visualization, but the ability to detect anomalies in telemetry and report them. In the example here, we have configured Grafana to send an alert message to our Slack workspace if the average CPU usage of a machine exceeds 50% for a period of time. This allows our team to quickly triage errors on the ground or in orbit as soon as they are detected. To minimize failure through automated testing, Midas takes advantage of GitLab's pipeline feature for continuous integration testing. These end-to-end integration tests allow us to validate our changes before we risk putting them into production on the ground or in orbit. Midas also connects to Slack, not only in combination with Grafana to send alerts when systems encounter errors. We have also connected GitLab to Slack to ensure that any errors during software development are reported. By increasing this operational visibility, these Slack notifications make it easier for new members to understand existing services and illustrates our development process. Midas also synchronizes upcoming passes over our ground station at the University of Michigan to Google Calendar. This integration also increases operational visibility and allows users to easily plan their day around the passes they will operate. By using modern software system design, keeping our applications small, networked, and developer-oriented, Midas has transformed MXL satellite operations for the better. In addition, automation, monitoring, and communication tools have proved invaluable for remote work during the COVID-19 pandemic. We can operate our ground stations, run our tests, and coordinate complex operations entirely remotely. Some next steps include creating automated command campaigns, which will be used to autonomously operate our spacecraft to ease the load on our operators. I'll leave you with results from our ETVEX mission. These payload operations were scheduled using Midas over ground stations in Bangkok and Ho Chi Minh. Thank you. Questions?
Okay. Thank you very much for the presentation. First question is, the use of modern software applications and services is compelling. However, it may present long-term compatibility challenges. How do you envision maintaining interface compatibility between the various third-party applications?
As I said, one of the core components of modern software system design is ensuring that applications are small, independent, and communicate over the network. This means that we can easily bring in new systems that stay isolated and can gradually be adapted to our existing interfaces. In addition, our development process makes it easy to add new features.
Okay. Which common data and telemetry standards, either commercial, government, or internationally based space institutions are implemented in your approach? So from an API, electronic data sheet interface perspective, which standards are you using?
Sorry, the question cut out at the end. Can you repeat the last sentence?
Oh, I'm sorry. Yeah, just from a standards and electronic data sheet, data sharing perspective, what standards are you using?
MXL uses its own internal protocol called the radio application packet. And depending on the types of radio application packets we ingest, we index our data differently. For example, we index telemetry with Grafana so we can see these different graphs, but we also download files to a separate database.
I guess specifically, is it CCSDS compliant electronic data sheet, machine-to-machine data, or are there other internal MXL formats that you're utilizing?
There are other internal formats that we use.
Okay. Let's see. While distribution of telemetry is a strength of the Midas architecture, how would you implement permissions-based access to telemetry or data that may have distribution restrictions?
So the authentication system that we use, which connects with Google, allows us to have different roles in our system. This also corresponds with permission systems in Grafana that allows select access to certain dashboards, so we can control not only who has access to what data, but who can view what panels in certain dashboards.
Okay, and one last question. Is your system able to also work with external data from other non-MXL satellites and/or databases?
So as I said, it's designed to be highly modular. So as we incorporate new features, the system is designed to be able to use telemetry data from any type of source. So we can also integrate telemetry from weather stations and other types of systems, not just satellites, into the Midas system.
Okay, thank you very much for your presentation, and I'll turn it back over to Marianne for closeout. Thank you very much, Michael.